Great. Hello, everyone. My name is Daniel Wyzorek. I'm a part of the Neonatal Asphyxia design team, and this is my honors capstone project. Okay, so before we get into my project, it's important to understand what neonatal asphyxia is and exactly why it happens. It's ultimately caused by a lack of oxygen in the brain, leading to hypoxia, and this can be caused by several issues such as knotting of the umbilical cord around the infant's neck or prolonged delivery. And as a result, the baby can develop several symptoms such as seizures, become very pale, a decrease in heart rate and respiratory rate, lack of blood flow, and just an overall state of shock from the lack of oxygenation. Now, once the thing blocking the oxygen is removed, like for example, the umbilical cord is unwrapped from the baby's neck, the issue that arises is blood can really rush into the brain, kind of like a dam breaking. And this can just overwhelm the brain tissues and lead to brain injuries and for babies, especially developmental delays, disabilities, or other kind of neurological dysfunctions. So the current treatment for this is hypothermia therapy, and this reduces that rush of blood into the brain by slowing it down through cooling and help mitigate these negative effects. Okay, so what's currently being used in India is this glove here. Now, this glove is essentially just filled with water, tied at the end like so, and then stuffed in a freezer overnight, and then the next day is taken out and applied to a baby for cooling. So there's obviously a better, um, there's a need for a better and more effective and reliable method that applies a consistent temperature to babies for low resource communities such as the ones in India. So NAP is partnered with the Hasya Newborn Care Center, and they provided us with these cooling requirements. And the two that I'll focus on here are that the device must cool the neonate to 33 to 34 degrees Celsius, so a 3 to 4 degree drop in core body temperature, and it must take around 1 to 2 hours to cool the patient. Now, one of NAP's current solutions that was provided to me at the beginning of this capstone project is what we call the tube bed. Now, the way this tube bed works is the baby kind of lays on top of it, and then water is rushed into these tubes and kind of snakes around like so. And the water is cooled to a specific temperature so that when it rushes through these tubes, the heat will transfer from the baby into the water and ultimately cool the baby down. Now, the goal of this capstone project is to simulate this. And now the reason prototyping wasn't used was just due to the lack of reliability and prototyping services during COVID. So that's kind of why I chose to model this and simulate it. And the way I did this was I first only modeled heat flow and temperature through the baby's head, and that's it. Then I modeled fluid flow through the tube bed just by itself. And then finally, at the end, I coupled the heat flow and the fluid flow to get a combination of the two and an overall model of the entire apparatus. And then my goal with this model was to optimize the cooling parameters such as temperature, the cooling temperature applied to the baby, the temperature of the water, the radius of the tubes in the tube bed design, and then finally the velocity of water flowing through these tubes. So getting into the results of the simulations, this was just the individual heat flow simulation. And the way I did this was I pretty much just applied a cooling boundary right here. And this allowed for heat to kind of transfer out of this through this boundary. And this is, of course, an infant-sized head model from SolidWorks. And what I found from this was that 307 Kelvin number that we were looking for, it didn't reach it. The closest it got to it was around 308 Kelvin, and this was at a cooling temperature of 260 Kelvin, or around -13, -14 degrees Celsius. And obviously, when you're dealing with a temperature like water, -13 to -14 degrees Celsius is kind of hard to obtain without it solidifying into ice. And we obviously can't be shooting ice blocks into the tube bed assembly. That's just not feasible. So going into the next simulation of just the fluid flow itself, I initially tried to model Knapp's CAD design of the tube bed, shown here on the left here, and I ran into a lot of trouble. It was just really difficult. For some reason, it was producing a lot of complex, turbulent, wacky flows that my computer just really couldn't handle. So I ended up simplifying the model with some key simplifications. First, I made it shorter. I reduced the number of tubes. I made the geometry a little less complex. And finally, I chose to make it isothermal flow. So even though the water is absorbing heat from the baby, I chose that to make the temperature of the water constant. And we'll get into more of that assumption later on in the takeaways. But those were the simplifications of the model that I did. And what this ultimately resulted in were these flow distributions. Now, when the water initially goes into the tube bed assembly, like here, it's just regular flow through a cylinder, nothing crazy, really uniform velocity distribution. But what happens when it hits the curve is when you start getting deviations in the velocity distribution. And you ultimately get these stagnation points right around the curve here, and then a little bit of an acceleration on the other side of the curve. And that is ultimately going to be really useful for the team moving forward and just developing prototypes of fluid flow through pipes like this. And let's see. Yeah, so that was just the individual fluid flow. And then finally, when I coupled the two, I ultimately got this diagram right here, which pretty much just summarizes the project, that you have the fluid flow going here, and then it's pretty much sucking up heat from the baby's head and leading to this temperature distribution. Now, ultimately, this still didn't work, which is really unfortunate, but it actually led to an even a little bit higher temperature than just the individual thing, where the lowest temperature I could get was around 308.4 Kelvin instead of 308. So this isn't really feasible based on the couple flows. So yeah, my key takeaway from this project was based on this model, the tube bed isn't really a feasible option because it can't reach that required cooling temperature of 307 Kelvin. And of course, this model does have limitations. We talked a little bit about the isothermal fluid flow. Just we're not really sure what the device's capabilities are of maintaining a constant water temperature for an extended period of time. So it's unclear on how this simplification will affect the results of this model. But in terms of other limitations, for body temperature, the way I measured body temperature was just a volume average of temperature across the head. And I know this isn't the most accurate indicator of the overall core body temperature, but it was really the best thing I could think of given the head model itself, and since we were just dealing with the head. And then finally, for metabolic settings, metabolism is very complex, and it's influenced by a number of factors, especially for babies who have a large amount of heat loss that can really influence metabolism. And the way I chose to model metabolism was really simplified. I just used a predetermined constant that maintained a core body temperature of 310 Kelvin at room temperature. And obviously, a constant isn't the most ideal, as metabolism can fluctuate over time and throughout the period of the day. But that was the setting that I used for this model. So that could also be a limitation as well. In terms of next steps, if someone were to continue this project after me, they could potentially use this model to assess Knapp's other current prototype, which is a waterbed. I initially considered using or modeling this waterbed assembly, but the geometry was just a little too complex. The fluid flow was a little too complex to initially start off with, but I feel like now that the foundations are built, my model could definitely be used to assess the performance of this prototype as well. In terms of acknowledgements, I'd like to give a special thank you to Dr. Robo, my capstone advisor. She was really helpful throughout the process, and and keeping me on track and just helping me out. And I'd also like to thank the Neonatal Asphyxia design team. They really provided a strong foundation for me to build off of and continue my work on this project. And then finally, I'd like to thank the Engineering Honors Program. It's for their support these past 2 years and just allowing me to complete this capstone project. So thank you, everyone. And yeah, that's it. Thank you guys so much for watching. Bye bye.